Thanks for attending. That's the joint work with Maxime Garnier, Dominique Leichler, and Luca Music. And we are going to talk about verification of quantum computations, but trying to remove some of the assumptions that are actually making it hard to implement in real systems. So just the setup is very simple. It's a quantum prover interactive proof system. So the idea is that we have a verifier who wants to obtain a bit from running a circuit over some inputs. So it wants to get bit B, but the problem is that this verifier just has limited power. In fact, it's a classical verifier. It's a BPP machine, plus at most a single qubit register so that it can prepare and send some qubits there. So of course, it cannot run the computation it wants to have the result of. So it's going to be asking for help to a prover. So the prover is a BQP machine, so it can run the circuit, obtain a bit B, and transmit that to the verifier. The problem is that, of course, the prover can be malicious, and so we have no idea whether the prover will send the bit B that really corresponds to the computation. And the task of verification of quantum computation is precisely this one: how to design a protocol so that you ensure that the bit B that you get from the prover is actually corresponding to the computation that you delegated. So this question was, has been asked like since long ago and solved in two different ways by different techniques. One is giving you information theoretic security. The other one is basically relying on computational assumptions. What makes the difference between the two is really the requirements that you have if you want to ever implement this kind of protocols. The requirements for the information theoretically secure solutions is that the verifier really needs to be having this small quantum register. Okay? It cannot perform useful computation with it, but it needs to have it. If you rely on computational assumptions, then you'll be able to have a fully classical verifier. But the problem is like the prover will be more complex. Okay? So if you want to implement this, you have a larger overhead on the prover, plus the fact that you don't have like unconditional security. You can, refine this and add more properties here, but what I'm going to be interested in here is really like trying to lower the requirements on the verifier side in the information theoretical secure setup. So the motivations, let's be quick. Okay, it's foundational because it's one way to possibly design experiments that could falsify quantum theory. But from a more practical perspective, it's also exactly the situation where the verifier is actually an end user trying to delegate the computation to a powerful server. Okay? And it doesn't want to sacrifice privacy nor integrity of the computation. There, it also wants something cheap, right? So it wants this to be efficient. So it wants that the security error is negligible in the added overhead to gain this security. Imposed by the protocol. It also wants to have something that's scalable in the sense that you want the security error to be controlled and not grow too large when the computation size increases. So that's the two important requirements. The last one is also cost effectivity. You want simple hardware if you ever have to implement this kind of situation and protocol. And in this talk, what I'm going to do is to show you that, in fact, you can remove the necessity of single photon sources if you imagine that the verifier is having single photon sources. And so I'm going to remove this necessity and replace it with just attenuated lasers. Okay, so I'm basically doing a theoretical proof that incorporates some of the constraints from hardware. Okay, so we could call this a hardware-efficient proof. So it's simpler devices, faster devices. It's more cost-effective because, like attenuated lasers, you can get very good ones for not so much money. And it's also a prototype setup for dealing with less powerful and partly imperfect devices. Okay? So how can we go to the solution? Well, maybe just give you a short overview of these information theoretical secure protocols for verification of quantum computation first. then we'll see how we need to modify a little bit the protocol so that we can hopefully manage to use weak coherent pulses, but unfortunately we'll break the security badly. Okay? But informed by the way it's broken, we'll be able to find a counterattack and recover, in fact, the security by using something that I would call like fully quantum privacy amplification gadget. So it's a little bit different than what you have when you do QKD, because here we do the privacy amplification at the quantum level. Okay? So we work on quantum states and not with bit strings. Okay, so let's go for the overview of the verification protocol. So it makes my life simpler to just present this using the measurement-based quantum computation model. But as you know, MBQC is fully equivalent to the circuit model, so I can switch back and forth. So I'm not losing any generality here, but what I'm going to use is the fact that in MBQC I just have control Z gates, Z theta gates, and measurement along the X axis. Okay, so it works by representing the computation as a graph. Each node is a qubit. You have edges there that correspond to performing control Z gates between these nodes. These nodes were initially prepared in plus state. And you also have a measurement angle. Okay? And so this measurement angle here, let's say it's alpha for the first qubit, beta for the second qubit, and so on. It's what's in this black box here. Okay? So that's performing my computation, as long as I can also modify the angles of measurements informed by the outcomes of previous measurements. Okay, so that's the initial step. The second step is that I can realize that, in fact, I can modify my circuit here by incorporating some pre-rotation just after preparing the plus state. Okay, so I can input here some Z theta gates for a value of theta that is random and chosen independently for each of the qubits. Okay? So if I do this, I modify the computation, of course. But at the same time, you realize that I can counteract the effect of this Z theta initial pre-rotation by performing an additional Z minus theta on the other hand here. And the reason is that my Z theta commute through the control Z gates. Okay? So if I'm doing this, I'm apparently doing something that's useless, but at least it doesn't change the computation. But this useless thing becomes quite nice when you imagine that this is your, the circuit that is going to be delegated. In fact, what is going to happen is that you are going to have your verifier prepare the plus states, do the pre-rotation, okay? So that's going to be private for him. He's going to send the prepared state, the plus theta state, going to send that state, and then the prover will actually perform the control Z gates and will be instructed by the verifier into performing the last Z theta and plus alpha gate that is going to be compensating for the pre-rotation. If you do this, then basically the prover will just see random measurement angles that are being instructed to him by the verifier. And in this way, he will be completely blind to the kind of computation that you are trying to perform. Okay? But this is giving you a very powerful tool to compensate your lack of quantum ability as the verifier. The reason is that you can show that among all the possible angles of measurements that you can have in your initial computations, you can choose some of them so that the computation is classically easy to perform, and it's also having a deterministic result. And this means that basically, if you choose these specific angles as verifier, the verifier can know exactly what is the result of this computation, and it knows that it is deterministic. It's not very useful for making solving a use case, but at least it knows the results there. But now you can see me coming as like, well, if you use a computation for which the verifier already knows the result beforehand, he's going to be able to probe the behavior of the prover in this way. It's going to delegate blindly such deterministic and easy computation. And if the prover doesn't really follow the instructions, well, it's going to be messing up with the result. Okay, so there is going to be a given probability that the result is not the one that is expected from running the circuit if you are honest. Okay, so that gives the possibility for the verifier to actually probe the behavior of the prover. Need to work a little bit more to ensure that there are enough measurement angles that you can choose so that you can, with this kind of scheme, detect all possible deviation from the instructions that could be performed by the prover with constant probability. And then the protocol just follows very simply from there. One way to do it is just like you are going to take capital N rounds. You are going to choose D of those at random to perform the computation that you really want to do, for which you don't know the result. Okay? And for the other ones, you are going to choose randomly some of these tests, these computations that are easy and deterministic. Okay? And you are going to blind delegate each of the rounds to the prover. Okay? And in the end, what you are going to do is to look at how many tests are failed. Okay? So giving you a result that you were not expecting. And if it's low enough, and here this 25% comes from the colorability of the graph that you are using. So there are like universal graphs where the graphs are too colorable, and then you get like this 25%. So if you have less than 25% failure rate on the test rounds, minus some delta for the buffer for accounting for the statistical fluctuations, well, you'll be able to verify your computation with any desired accuracy, and the security error is going to be decreasing exponentially fast with the number of repetitions. So this capital N. Okay, so you know how to perform verification of quantum computation. But what you can realize here is that I really need to have this plus theta state pre-rotated by the verifier, and that this value of theta is not leaked. Because if the value of theta is leaked, then you can recover the initial measurement angle, the one that I'm delegating to you. And doing that, you'll be able to know whether you are being probed as a test round or if you are computing. Okay? And if you know where the tests are, well, you know, you are going to be behaving well on the tests and doing something funky on the computations. So that's something that you would want to avoid. Okay. Let's see what happens if, instead of my single qubit states, I use weak coherent pulse. So weak coherent pulse is the state of the laser. It's a mixture of the vacuum state, single photon state, and two photon states, and so on. And you can view it as really, you know, you sample an integer k from a Poisson distribution that depends on the intensity of the laser, and you prepare k times the plus state. Okay, so that would be the state out of the laser. Then you can rotate that thing again in the same way using phase shifters. If you try to use this state directly as honest player in the protocol before, the problem is like most of the time you are going to send the vacuum state. Okay, and if you send the vacuum state and input that into something that you think is going to be creating your graph state, well, it's not going to work, okay? So you are messing up your graph state. So you need to allow for the prover to just say, well, you sent me the vacuum state, please resend me some qubit because I lost this one, either through the fiber or it was just not sent. Okay, so you need to allow the prover to ask for a resend, and that's going to be problematic. That's going to be problematic because if this prover is dishonest, then what happens is that he's going to constantly, each time he's obtaining either the vacuum state or a single photon state, he's constantly going to ask for a resend, okay? And he's going to only work with 2 and more photon states. And then if he has two and more photon states, well, he has definitely the plus theta state that he was supposed to get, but he has an additional copy, at least, or several additional copies of this plus theta state. And he would be able to use these extra copies to actually infer some information about theta. And as I just argued before, by having some information about theta, he would be able to distinguish whether or not he is being running a test round or a computation round. So basically, the security just collapses. Okay, so you need to counter this. And the counterattack is actually this gadget that is performing some phase accumulation. Here, instead of just sending plus theta states and trying to use them directly, instead of this, we are going to do the following. We are going to say, oh, you want one plus theta state, but actually to get one plus theta state, I'm going to ask the prover to take capital K plus theta states that the verifier is generating. Okay, so it's sending these plus theta states, and it's combining them through this circuit. And this circuit just really performs like a sum that depends also on the measurement outcomes here, but it's basically a sum of all these thetas. And what you realize from there is that if there is just one single plus theta state that has a single copy of the plus theta, so it's coming from a single photon pulse, then it's enough to completely one-time pad the sum. Okay? So basically, if you are trying to infer some information about theta here, and one of the theta I is missing, then you are screwed. Okay? So that's what is going to help you in recovering the security, because now if you are trying to attack the protocol using this gadget, that's entirely performed by the prover, that means that the prover needs to really reject all the states that are 0 or 1 photons. It cannot work with 0 or 1 photons. So basically, you have discovered what is the optimal attack with this thing. And using this optimal attack, well, you're regaining security is not very complex. You just ensure that you cannot be a successful cheater and at the same time pass an additional statistical test based on your ability to actually have these k copies of k versions of the plus theta state. So just to give you like what this kind of check looks like, well, it's very simple. At least when you use one single intensity for the laser, basically what you want is you want to count the number of events that have 1 photons and more for a given intensity. And what you want is that this number, for the version where you are really using the attenuated laser and the lossy fiber connecting you to the prover, and the prover is honest, you want that this number is large enough so that you can actually perform this gadget. So you have k of them, plus some buffer again to accommodate for the statistical fluctuations. So that's giving you the correctness of this thing. And then what you want is that you cannot have a successful cheater there. So the successful cheater would try to only work with 2 photons and more, and it's also able to actually improve the situation by removing the lossy fibers, so to get even more 2 photons events. Okay? So what you want is that this number, which counts the 2 photons and more events, is smaller than k, again minus some buffer delta. Okay? And then it's a game of playing with the probability distributions to make sure that these 2 events are basically disjoint, and there is this gap there. And you are going to fix your value of k just in the middle of the gap. Okay? If you do this, well, of course, you need to tune this capital N, the k, and also the intensity nu to the value of eta. And what you get is a dependency in the number of times you need to press the button to generate a laser pulse. So this capital N grows as 1 over eta to the 4. And eta is the transmittance of the fiber, which means like it's basically 1 over eta is basically something like the distance. Okay, so that's not very good scaling with the distance. Well, you can go to more. Oops, sorry. You can go to more intensities. I'm just like skipping this, but going to more intensities give you a better scaling. So 1 over eta squared. Okay. And just like going to the conclusion, so what we have in this, work is a composably secure verification with laser pulses. So our experimentalists are very happy to be able to work with lasers instead of single photon sources. We have improved over previous versions of just the blindness by going to the 1 over eta to the 4 to 1 over eta squared. It's also giving us like a generic template for proofs in the multi-intensity setup. And it's close to, but quite different nonetheless, to the decoy state method in QKD. First, because it works at the level of quantum states. Second, because there is just a single honest party, so it changes quite a bit the proof techniques there. And because we look directly for composability, we have like stronger requirements on the finite size analysis. And so we are not able to use some of the results of the decoy state methods that are a bit too optimistic in our scenario. And with that, I thank you for your attention. Well, yeah, there are some open questions. What can you do beyond 2 intensities and still improving on the verifier and provers requirements? So thank you again.
Thank you, sir.